All right, Ian, thanks for volunteering to lead today's discussion. I'm gonna hand things over to you. If you want, you can also start just by saying hi, say a little about yourself.
All right.
Not required.
Let's see here. What do I got here? Share screen, Alt S. Let's try that out. Screen. Most tend to use that one. All right. First, about me. I am just a guy, more of a hobbyist, not really professional. I kind of been attending the San Diego machine learning meetup for a little bit, trying to get more involved, trying to break out of my comfort zone. So here I am. And some disclaimers. I am a very awkward, anxious guy. So these sorts of things, not really my proclivity, but trying to make the best of it. And the way I see it is, whoever's coming after me, you can learn from my mistakes. We can, figure out how to do this better. I know that Ted and Ryan kind of have their jam down. They've been doing this for a little while, so it's like automatic for them. But for the rest of us, it's probably good practice.
Mm-hmm.
So thank you, Ryan and Ted, for providing this opportunity. And then what's a second disclaimer? I'm on Windows, and I'm usually not on Windows, so this is a little weird. And also, I haven't done a webinar or anything in like years, so if I bumble around with Zoom, that's that. Anyways, so chapter 2, the end-to-end machine learning project. The first thing they lead off with, the author leads off with, is the machine learning project checklist. I just copy pasted the version from Appendix B, but it's essentially the same thing that's in the start of the chapter. And it, lays out the general steps that people tend to, go through when tackling a machine learning project. It's all pretty, basic stuff, frame the problem, look at the big picture, get the data, do some EDA, prepare data, expose patterns, try some basic models, etc. And of course, it's, pretty customizable. Not all these steps are going to be relevant to every sort of machine learning project. But, for the most part, and especially at the level of this book and tabular types of problems, this checklist definitely kind of holds true. Having, read a bunch of other machine learning books and taken a bevy of online courses, I, did notice that there were similarities with other checklists. Like, Andrew Ng tends to have a lot of these sorts of similar flows or diagrams or checklists in his course material on Coursera. I think he's got a new ML Ops program that a lot of people are enjoying. And you'll see that, his kind of laid out flow is pretty much similar. One of the only sort of notable changes is that there's a little bit more emphasis on the labeling and organization of the data. That, of course, is very relevant for the sorts of problems that he tends to work on: deep learning stuff, computer vision, segmentation, language models, things that don't always tend to have the labels readily available. But again, for us, we're not so concerned with that. And hey, just a moment, Ted, you tend to use Google Docs, right? Do you put it in presentation mode, or do you just kind of scroll around?
I haven't ever used presentation mode. You can. It's mostly just sort of maybe, I don't know if it's a little bit small for people. I don't know if there's a Zoom.
Yeah, that was kind of my concern. This is one of those learning by trial and error sorts of things.
I can see it fine. The size is great for me.
Yeah, it looks like a good size to me.
Okay, well, that's good to know. I always got to be aware of that. And, I have a bunch of those sorts of concerns because while putting this together, I was kind of going like, okay, well, what's the best way to do this? I could bounce around between the book material outline and the notebook, but that could be a little bit discombobulating. And so I thought, hey, we've all we can read chapters. How about I just combine bits of both, and then interspersed with some various tips and things like that to spur discussion. So that's kind of my approach to it. And
Yeah, that sounds great. There's no right way. So
I'm also hoping that all these graphics aren't like pixelated to hell, like potato quality. All right, so the author basically sets up a situation, a fictitious situation where we are employed by a real estate company, and they provide us a data set. And this is a classic data set, the California housing prices data set. Apparently it's from some StatLib repository. I'm not familiar with that, but maybe some of you are. There's a few notes on that. It's based on 1990 California census data. So it's going to be like, wildly inaccurate or unrealistic at this point. But it's all numbers. These are all abstractions. So we can deal with that. Also, the author removed some features and added a categorical feature. They just did that to, for educational value. That may be something to kind of keep in mind if you've seen this data set before, or use it in the future. It's not going to be exactly the same. And then a point of confusion, or at least possibly, is that the examples, the rows, are they're not individual houses. We are dealing with districts or block groups, and those are defined, at least in terms of the census, as smallest geographical unit, which the U.S. Census Bureau publishes sample data, and so these could kind of have varying size and density. All right, so the chapter goes through pretty much almost all the steps in the machine learning checklist they provided. First up is frame the problem. Now, for practicing data scientists, usually the first step is to talk to people. Find out who has your data, who manages your data, where the data is coming from, who's worked with it in the past, how it came to be. Also typical things like what the expectations are for the project, what they want, and also, considerations for who's using it downstream. So, the first step is just to gather as much information as possible. And that usually requires talking to people. So, we want to nail down a business objective. And of course, the author notes that, the business objective is kind of important because it sort of determines other decisions you make. Is it going to be classification, regression, and basically a bunch of decisions all down the pipeline.
Hey, Ian, can I make a quick comment here?
Mm-hmm.
So my experience with talking to business stakeholders is that generally they don't understand machine learning. And a lot of the people I talk to are not really senior people in business. And so they don't really understand business objectives either. And so, for example, I work with, we call the schedule appointments, right? And so basically what someone will say is, okay, build me a model so that more people schedule appointments. And that's not something I can do.
I know that tends to happen a lot. And also there's sometimes what you're told the objective is not the actual objective. Like, is your objective to increase traffic or is it to increase sales? There's a difference between those two things. Just like there's lag in lead indicators. And so you have to be mindful because, your project owner could tell you that the objective is whatever, but you could very well end up, probing them further and finding out what they really want is something else. And maybe that something else is something you could have done easier than the original objective, or maybe even it's not feasible at all. So, a lot of value in talking to people. But luckily for us, they provide an objective. The objective is to predict a district median house price. So given an arbitrary district, we want to predict a median house price. Now, of course, the true objective tends to always be turn data into money. That's usually what we're doing, unless we're like Hobson and we're doing altruistic fun stuff. Then and so the author kind of provides us with some other kind of details that are important that we would have acquired through gathering information and whatnot. So our predictions are going to be fed to another system. That's of course important. We don't want to muck things up for them, and we want to provide them what they need. And they tell us that district house price is currently estimated manually by experts. They have a team of people. They go out, they survey, and they use complex rules, and it's time consuming, and the estimates are bad. So we just want to beat their poor estimates. That's not like so unreasonable, but maybe it is. We'll see. And the owners of the downstream system confirm that they want a numeric value, not a coarse-grained approximation. That's the whole, is it a regression problem or is it a classification problem? So the determinations, we have labels, thus it's a supervised learning task. We're trying to predict a continuous target, thus it's a regression problem. And we're only predicting, one target for each example. So it's univariate. And, this is a note that it was actually in the footnote, and it's something that I did not stumble upon for quite a while. I'd known about the, I guess the regression to the mean fallacy and stuff like that, but I never really put together that, regression and, lines of, best fit and regression to the mean had a relationship. And I guess they're all come from Francis Galton and his observations. But moving on, so the next step is to kind of define how our model is going to be evaluated. How do we compare models? How do we tell when we've met our objective?
Sorry, Ian. Can you post the link to this in the chat, or how do I get to this?
Oh, sure. Let's see here. I think I could just restrict only people. Change to anyone with link. Copy link. Meeting controls. Chat. Hopefully, copy paste is all enabled.
Awesome. Thank you.
You're very welcome.
Shouldn't be eventually put to Ted's GitHub account?
I mean, if he wants, it's it's totally up to him.
Sure. Yeah. No, we can do that.
They give us a performance measure. Because the book is kind of aimed towards newbies. So the assumption is not everybody knows all the metrics and all the loss functions and all that kind of stuff like that. So they gave us a pretty much the bog standard measure, which is the root mean squared error. And, I had always known this from mathematics circles as the L2 norm. And of course, 2 is just that index. Indicating that they're squaring the errors there, the residuals. And just for the sake of being clear with notation, m is the number of instances, so that's the number of rows for us. X superscript I is a vector of all the feature values, and then we have a y superscript I, which is the label, and then in this, they use the H as the hypothesis function. So that's basically, like our model. We're proposing that our model is going to be of a specific form. And then, our predictions are by convention usually labeled Y hat. And for anybody unfamiliar, like this is the very rudimentary illustration of, how some of these things are intuitively kind of calculated. We have residuals, which are individual errors between, our example points, our training points, and our proposed, function. And then, with those residuals, we end up squaring them, summing them, dividing by the number of them, and then doing a square root.
Yeah, I have a question around here. Actually, so they are in a book 73. So they are kind of flipping that, so notation, not notation, that so they are scores, so negative scores, and then taking a square root of it. Why is that? I mean, the book kind of explains it, but I didn't get a clear picture of it.
You're talking 73.
Yeah, at the bottom of this book, at the bottom of that code. So NumPy dot.
Oh, are you talking about further down where they use the negative mean squared error in the cross valve?
Oh, did I went too fast? Sorry, but yeah. So.
Oh, yeah. They made a note about Scikit-Learn's convention where
I wasn't quite understanding it.
They use a utility function rather than a loss function. So basically, they're kind of flipping things, and to get a positive value, or to get to make things turn out the way you want them, they have to add that negative there. There's ways around that, actually, which I found kind of interesting that the book did not really highlight, but I guess it's not that super duper important.
Okay.
The scores, the cross-validation function is set up to find the maximal value of a score. Score is a loss function in general sense. So if we want to minimize it, it won't do it for us. The way, technical trick to force it to find the maximal value, if you want the maximal value, is to take negation.
Okay.
Yeah, that's definitely a succinct way of putting that.
But if your score is accuracy, you don't need to negate it. You just wanted the highest.
Okay.
Yeah, I mean, there's definitely some roots in optimization and convex functions and things like that. But for some newbies, there could be some questions about why this metric was chosen, and why the parts of it. So the squaring penalizes errors, large errors at least, and that could be something that we want to happen. Another detail that comes up a lot in machine learning courses and literature is the fact that when used as a loss function, it's easy to differentiate, and that's very important for any of our gradient-based methods. As for the square root brings us back to natural interpretable units of the problem. So rather than squaring things and staying with a unit squared, in the end, they take the square root and basically squash that back down and retain our units. And then there's the whole question about why root means squared error and not mean absolute error, or something like that. Well, I mean, again, that has to do with the norm index and what we are prioritizing. Mean absolute error can be preferred for a lot of problem for a lot of situations, especially when you have outliers. And so,
Ian, I do have a question here. This is Becky, maybe for the group. I
Becky?
wonder how often in our actual practices we look at the distribution of the errors. Like when you say like if we know there are plenty of outliers, we're still thinking about the actual data, right? Not the errors. So
Yeah.
do other people have some experiences about like how often do you actually look at the distribution of the errors, not just the distribution of the data?
You're talking about, okay, the distribution of errors. Well, I mean, that's definitely important for what, linear regression and
Right.
ordinary least squares and whatnot like that.
Right.
You know, in order to have those theoretical guarantees that they provide, you know, which is kind of one of the great benefits of using those more simplistic models, is that, you know, your residuals have a certain, you know, nice distribution, and, you know, all those other properties of the Gauss-Markov assumptions. And I mean, honestly, I don't really check it that often unless I have reason to. How about anybody else?
I would say for simpler models, I definitely check the distribution of the errors of the residuals. First, you know, I want to make sure that there's not some obvious pattern there, because then that would imply that, you know, I might need to do something with my features. And also, you know, I'd expect them to be kind of balanced and whatnot. But if it's something like a Kaggle competition, then also, like, oftentimes a small number of examples are contributing a lot to your error. And so rather than trying to solve every problem, sometimes it helps you hone in on where are the places where my model's missing the most, where I'm getting penalized the most. And so you might be able to fix a small number of things and make a bigger dent than if I try and prove something that's already working pretty well.
I see.
Yeah, another thought on this concept of RMSE versus MAE is to note that RMSE is going to be a good metric to use when you care about estimating the mean, and MAE is a better metric to use if you care about estimating the median. So I would say that sometimes it might depend on your business case, or, you know, what does your cost function really look like at the end of the day? And does your loss function, in this case, the mean squared error versus MAE, does it match that?
I know an example when it actually worked well. In general, it is useful for logistic regression or for just linear regression. And it tells us that if, you know, they're well distributed, in meaning they're well behaving, then we can use statistical methods. Then p-value is reliable, for example. Other statistical values are reliable. And what you can do with it, you can compute confidence intervals.
Yeah.
But in particular, I know a case when, where was this? I forget the company, but it is here in San Diego. They needed to estimate a time which each engineer, not the time, they need to estimate resources which each engineer needed for project. And they needed to estimate not mean or median, because it would give them about a half. They needed to estimate it with some kind of overlap, like, you know, 95% of confidence interval, something like this. And they used linear regression for this.
So they're trying to get some reasonable bounds.
Yes.
Yeah. I know that's, you know, it's because of those theoretical, you know, niceties that, you know, insurance agencies tend to use, you know, linear models like that, generalized linear models, fancier versions that still have some, you know, statistical foundations. And because they have to explain their models to regulators, and they have to have some,
not
provide
only
assurances.
this, but they need to make sure that they not get that they do not run out of money. I didn't say it. They do not get bankrupt by each claim, because they need to, for each driver, to pay a little bit above the medium. So they will have this, safety pillow. I actually studied it at some point. By the way, I studied actuarial science.
Oh, yeah.
And they explain it quite in detail why they need it and how they do that.
Yeah, I know that's quite a deep field in what they have.
So Maya, are you saying that in that particular case, it was better to use mean absolute error over root mean square, or which one was preferable in your example?
I don't remember which statistics, which methods and used, which metrics and used at this point. I think they use logistic regression because mean absolute error is not very stable as a method. It may have several different models, which for this particular data are more or less the same, but they may differ quite widely on a test data set, because it is different data set. So in this sense, just usual L2 metric,
Okay.
much more reliable.
But I'm also wondering, by my question about what kind of data transformation that we may consider doing, right? Even before we get to the decision on the measurement of the performance. Like, have you guys all considered something like Box-Cox transformation?
Yeah, look power and box Cox and yep.
Okay.
But the thing is like our model choices are going to play a role in what our pre-processing decisions are. Like, if we're going to use a linear model and we want those statistical, theoretical guarantees, then we have to abide by those. And so, we would want to ensure that our input features are, roughly normal, Gaussian. And so in that case, we'd have to use something like, a Box-Cox power transform or a log or some variant of that in order to rein in those long tail distributions. But in a lot of cases, we don't need to do that. So it all depends.
Good, thank you.
I just had a small question, Ian. If you go back to previous page in which you say that the reason why we square is to also penalize the deviation, something like that. Yeah, to penalize large errors. I'm just trying to regression and lasso when we have those the terms that penalize those. So could you help me?
I mean, lasso lasso refers to the regularization. Yeah, that's just that regularization is just a modification of the loss function. And so, yeah, they are doing well, what they're doing is not penalizing errors in that case, but penalizing the absolute magnitude of coefficients. Let's see, a ridge regression is L2 and lasso is L1, correct?
Right. Yeah. And so people use the word penalize for both, but like Ian just said, it's different contexts. So in this case, let's say you're just doing a simple linear regression, okay? You could have a slope that's like this or a slope that's a little bit different. Which one should you pick, okay? So let's say one of them gets a lot of points really close, but is way off on one point. And the other one is not as close on all the points, but doesn't have any that are too far away. what Ian's saying is that because this squaring thing penalizes large errors, it's actually going to pick the line that's close to a lot of points. Just I'm using very broad generalizations here, more than it's going to pick a line that's super close on as many points as possible, but possibly way off on a couple. Okay, so in terms of what is the optimal line, that's what it's going to pick. Okay, if you used an error like mean absolute error, which has no square term, then actually it would be more like tending to pick the one that was the closest to the most, because it's not really going to heavily have a large error associated with points that are way off, not as large an error.
Yeah, thanks.
I just want to add that lasso regression is very interesting because what it does in reality, it drops variables which bring mostly noise and not much of a value.
Yeah. I like lasso. Then of course, you know, also to be noted is that you know, Scikit-Learn has the elastic version, which is just, you know, a combination of the lasso and the ridge. And so, you know, you could kind of optimize those the regression, each aspect of the regression, you know, independently, if you so choose.
And on a similar note, if you're worried about the errors rather than the coefficients, you can use a combination of L1 and L2 through like a loss function, like a Huber loss as well, which is available through most packages.
Huber loss. Now I've heard of that. Is that the loss function that's used in ElasticNet, or is ElasticNet like literally just a combination of L1 and L2 regularization along with?
My understanding is that ElasticNet is just the combination of L1 and L2 regularization of parameters, while the Huber loss is more concerned with the errors, the regression errors. Okay. So what it does is it's saying we're considering this trade-off here, right? We want stability, and so the MAE, one of the disadvantages of MAE is that there's no single stable solution, as Maya was pointing out, right? Once you get a good solution, there's an infinite number of good solutions that are equally good. And so the model doesn't really stabilize. But the flip side of that is that if you just do an MSE model, then you're going to get this effect where you might be overemphasizing one data point that it has a huge error.
Oh.
So to get the kind of the best of both worlds, if you will, you can choose a loss function that is smooth at the bottom, but that is otherwise shaped like an absolute value.
Yeah, it kind of, it's almost piecewise. Yeah,
yep, exactly.
You see the same thing in certain activation functions used in neural nets, where they want to mitigate for things like dropout, but yet they still want the loss function to provide some dynamic results. Does anybody ever see any choice other than index 2? I mean,
sorry, just to be clear, index 2, that's lasso. Or no, lasso is index 1, right?
Oh, well, right here, I'm referring to the index in the metric or the norm being like the squaring. Like you could potentially do a cube or so on. Of course, they'd penalize things more towards the high end, but I've never seen it.
Okay, we have separate things here. One thing we have a metric which could be L2, and we can have regularization or L1. We can have regularization which is L2 or L1.
Thank you, Maria. Yes.
Yeah, it's mix and match. Yeah.
Yes.
But
so sorry, could Maria, you distinguish the difference between regularization and what?
And metric itself, the loss. Regularization, did you see a formula for regularization?
They don't have it quite yet. I'm sure it's going to get to it in like probably the next chapter than the one after that.
Okay, let's wait then.
And then another chapter on regression where they probably go through a few more formulas.
Okay.
So chugging through here, the author makes a suggestion, check assumptions again. You went through this kind of data gathering process and problem formulation, but you really got to make sure that you got that down. So, go talk to people again. For the sake of time, I'm going to skip something I thought was interesting, which was a note on pipelines. A pipeline is just a sequence of data processing components. The author states that components typically run asynchronously, but I don't necessarily think that's true. I think a lot of components have sort of dependencies. You obviously are not going to run a model until you have at least a batch, and so on. So I think there's kind of some nuance there, but it's not super important for us right now. So chapter 2 was get the data, and they provide a few different ways. The place to go would be the GitHub repo for the book. In that, they provide some links. You can just click on this, the open in collab, and it works. I ran through the entire notebook, no errors, no weirdness, nothing to be alarmed. It works totally fine. The only thing you have to be aware of is that if you want to save your work, you got to save your work. And then the author provides actually a bunch of command line for installing Python and getting a VM up and running from the ground. I thought that was a little antiquated. I think that's good for some people, but if you want to run things on your own machine, you should probably just use Anaconda or Miniconda. It's all nice. You got the Conda package manager. It comes with a bunch of stuff. You got Jupyter Notebooks, Jupyter Lab, a bunch of other helpful things. That's just the way to go. It's all managed nice and easy. As I said, less preferred, VM, virtual env, etc. And if you are feeling like super spiffy, you could try Docker. You will find that using a Docker image is extremely helpful if you do anything that requires something like a GPU. If anybody has experience installing NVIDIA drivers on a Linux system, it can be a super bummer. And having a preset Docker image where your Conda or your CUDA and all your subsequent necessary libraries are nailed down is kind of handy.
Sorry, Ian, just very quick question. I can Google this, but just quickly.
Mm-hmm.
At a very high level, you mentioned those three things: Anaconda, Docker, and something else. What are those?
Anaconda is it's a distribution, and by distribution, a Python distribution, what it means is that it packages your Python binaries and a bunch of tools and a lot of the main packages kind of all together in one installable.
A library, basically. It's a library.
It's more than a library. It's like a whole bunch of stuff all together.
Gotcha. That's Anaconda.
Yeah.
What's Docker?
Docker is it's a utility for providing isolated environments.
Virtual environment?
Well, it's sort of like a virtual environment, but it's actually more like a process level, or there's another layer of abstraction.
Gotcha. And so, sorry, quickly, and what's a Jupyter? How does Jupyter fix?
Jupyter is our notebook system. So rather than use a traditional development environment like IDE, like I don't know, Spider or VS Code or PyCharm, a lot of data science people tend to use something called Jupyter Notebook, and it's an extension on IPython, and it basically lays out your code in cells, and you can run these cells sequentially, and it's handy for testing, prototyping, things like exploratory data analysis where you're doing lots of plotting and stuff like that. So you'll notice that within Python people, the data science people tend to use notebooks a lot more. Traditional Python developers, using web technologies are gonna not use notebooks so much. So people use different tools for different purposes, but you're gonna see Jupyter notebooks or some variants everywhere. either on your own machine or on platforms like Kaggle. Their notebook system is basically just, a copy of a Jupyter notebook.
Oh God, that's what I was going to ask you. Excellent, thank you. Yeah.
Google Colab, it's just a copy of Jupyter notebook. It's the same kind of thing. And the author does provide a note about the importance of virtual environments. You gotta kind of keep track of your project dependencies and things like that. It really helps you organize things, avoid headaches and things like that. So the author uses, I think, virtual env to set up an isolated virtual environment. However, if you're using Anaconda, you're going to use the Conda package manager. So those are just both things that you should probably get used to seeing and using. I go through a few kind of situations and reasons why you'd want to do that. With virtual environments, you not only do you want to keep your dependencies managed, but it provides other benefits as far as sharing and basically just avoiding a lot of headaches. I already kind of went through this. Data science ML people tend to use Conda or some sort of distribution like that. Python people tend to go a little bit more lower level, VM, virtual env variants of that. This is kind of a gotcha. It's not going to be important until you actually encounter it. But when you're using things like Conda environments, you'll start out using Conda to install packages. Everything will be all fine. And then eventually you'll run into a package that's not, in an official Conda channel or repo, in which case you'll have to use the Python's pip or pip3. And once you do that, that can create some issues. And I've found, and I think Hobson also mentioned this in the past, that once you start using pip in your Conda environment, you might as well just keep on using pip, because Conda is going to have trouble resolving the environment. This stuff probably not super important right now. So, the author leads us through looking at the data. This is just a cursory glimpse at the data. And he introduces pandas, but doesn't really provide a lot of detail on it. Pandas is one of the very, very popular data science packages in the whole Python data science ecosystem. It's, it provides an object that is essentially a table. It's an Excel sheet or, a database table. You can think of it just like that. It's got columns, it's got rows, it's got some column labels and some other niceties. So, one of the first methods people tend to do when looking at a data set is, just do the old head method. Head is, kind of self-explanatory in that it provides the top. This can be useful or it can be not. If your data is ordered, then you're not going to see a lot of, you may not see a lot of variance, if we just go by the head output and look at ocean proximity, we may come to the assumption that all these values are probably ocean proximity. That would just be a false assumption. So an alternative is to do something like sample. And it'll just grab some, quasi-random indices and spit that out. That may give you a better cursory view of what's in your data. More thorough methods, we have the info method, and that provides a lot of useful information in terms of, how many rows we have. It'll provide you information as far as whether you're missing values, at least to some extent. There's some gotchas involved with that. It will recognize official nans or, things of that type, but it will not necessarily recognize placeholder values. So, if you were given a data set and they used some arbitrary number like -1 to denote a missing value, this method is not going to detect that. It doesn't know that -1 indicates a missing value or something like that. And similarly with string and categorical variables, it's not going to know what the placeholder is. So another thing to pay attention to here is that it tells you the data types. And that's useful, and it's good to kind of keep track of, because sometimes pandas can make the wrong assumptions when it's importing a file regarding your data type. And that can cause headaches later on. For people unfamiliar with pandas, they have the normal, numeric data types you may be familiar with in other languages, essentially. But when they have something, when they refer to something as a D-type object, it's typically a string or a text. Then, to address this issue before about, what exactly is in the ocean proximity column, we have a handy method called value counts. And that just, you can operate it on a series usually, but I am sure that you can operate it on a whole data frame, and it'll probably just give you some similar output. From that output, one of the important things to notice is this counts down here in the island category. We only have 5 examples. That's something that could be kind of concerning later on, because maybe we don't have enough island type data in order to to satisfy our model's needs, or maybe it's bad data. It's just something to kind of keep tabs on when you see small categories. The describe method is extremely popular. That gives us counts, means, standard deviation, min, max, and quantiles for all our numeric columns. This is handy because if you want to just get a verify whether or not there's any kind of strange values on the low or the high end of any of your columns, this will usually tell you. You can also get an idea of how skewed the distribution is. And then the author introduces us to our first kind of basic plotting, and that's the histogram. Histograms are an approximation of the distribution of numerical data, and it's basically just it's counting how many values of are of value 34, how many values are of 38 or whatnot in latitude. It just counts, bins, and gives you that output. Now there's things to look out for. So we're concerned about lines and cutoffs. You can see that here in housing medium age right there. What's with this gigantic line? Why there's so many at approximately 52 or something? That's very concerning. It could indicate problems in data collection, corruption, and abused data pre-processing. These can cause a lot of headaches later on. So these are what we're looking for. You'll see that also median house value has that. And that is bad because that's our target. So we're also looking for basic known distribution types. Again, that's just because we have more tools. We have more theory available when we have known distributions. If you have a wacky, bajillion modal distribution or something just, bizarre, what can you really say about it? You can just get a rough kind of idea of centrality and dispersion. I guess there's, non-parametric statistics, but we don't need to go there. Also, you're looking for very pronounced skew, something like that, where you have a long tail that really just kind of jets out. one way or another. So the author makes some notes about, what to kind of take away from these histograms. One thing is that the median income does not seem to be in US dollars. Median income right there. 15. What the heck is what the heck is a median income of 15? That doesn't really make sense. Like, clearly that's not right. So they give us some detail on that. It's of course kind of capped, but we can at least deal with it. It's an example of a pre-processed feature. That can be common when you're downstream of whoever provided the data and they made that decision. I don't care for when people do that, but maybe they have reasons. Another note: housing median age, housing median house value. It's all capped. Attributes have different scales. By scales, it means kind of the range of values. You can see here that we have a 0 to 500,000 here as far as our target. But in terms of our features, we also have kind of wide disparity of scales. 0 to 6,000 versus something like, I don't know, -124 to -114. Those are kind of wildly different, and that can cause problems. Something that sometimes I forget about all the time. This is for the newbies. Left skew versus right skew. It's kind of good to visualize this. Basically, where is the mean in relation to the median? That's kind of what you have to remember. It can be kind of counterintuitive because you see the density kind of leaning to the left, yet this is the right positive skew. But again, you just got to keep track of where's the mean. Well, the mean is to the right on this one. And with this one, the mean is to the left. And just a quick warning about histograms. They can be deceiving. There's a good, medium towards data science article that has some good graphics here. How histograms look can change depending on how many bins you chose. This is all the same distribution, but you can see they look different based on how many bins. You could plot this and be like, oh, it's a somewhat normal-ish distribution. And then if you used 19 bins, you go like, oh, wait, is that bimodal? What's going on there? And so you got to be kind of concerned about things like that. Similar situation with, maximum values. A slight change in maximum value could essentially reorder the points within bins and create drastically different looking histograms. Here's another kind of gotcha. Inappropriate bin width, same distribution, changes in bin width reveal kind of a different pattern. You go like, oh, that's totally fine. But then you look at that and you go clearly, okay, there's a whole ton of zero values that stand wholly separate from the other, mass of the distribution, and you'd handle those differently. So it's important to know about them. The author then goes on to, describe why creating a test set is important. By creating a test set, they mean basically partitioning the data set into two separate sets. One, a train set, which you use for your modeling, and the other, a train set, which you create and you set aside and you don't touch it. The reason being is that you want the ability to have a fairly unbiased evaluation. You'll hear about data snooping bias or data leakage. You want to be able to ensure that your model actually generalizes, and that wouldn't be the case if you just tried to kind of hone in and focus and overfit some specific data. So Scikit-Learn has some tutorials and some some kind of graphics about different splitting routines that they have that can be kind of helpful because you read the name of the splitting routine, but you don't like have an intuitive idea of what it does. Sometimes the graphics help. The author goes on a tangent about hashes and cyclical redundancy checks and basically lower level ways to ensure a reliable, stable splitting. I don't think that's super important. What is important and what you will commonly see is setting a random seed. You'll see this in Scikit-Learn. You'll see this in deep learning packages. It's kind of the standard way of ensuring reproducibility and kind of honing in the randomness under the hood. A lot of data science newbies may be kind of confused about why they're seeing 42, the magic number 42 everywhere. That's just some nerd thing. It's a reference to the Hitchhiker's Guide to the Galaxy. It's supposedly the answer to the question of the meaning of life, whatever. You can set that to your favorite number. Just be sure to, keep it constant if you want your splits and whatnot to be reproducible. The most standard data set splitting function they provide is the test or train test split. And that's just random sampling. So it's as basic as it gets. You specify how much you want the test size to be, and you give it your data set, and it's it'll spit out a test and a train. You can also provide not only a data set of the features, but a data set of the targets, and it will spit out another two. You do have to keep the order correct. If you're curious about the order, or you want to ensure, you could always just look up the documentation, and we have a good kind of example line. If anybody has some insight on the lower level stuff that the author kind of spent a few pages on in terms of hashing and splitting and things like that, I'm would gladly hear about that kind of thing. I'm completely unfamiliar with it though.
I can touch on that for a second.
Mm-hmm.
I would say in general, that's not a super common thing that I see very often, but basically what they're describing is when you want to do your train test split partition, whatever you want to call it, you want to set aside the same data every time, basically. And so one way to do that is with the index. And so you can just say, okay, always give me these certain rows. But then it becomes problematic if you have a data set that is changing underneath you. So it's not a big deal if you just have a single CSV file and every time you load the same CSV file, but it's different if you're loading in from a database or some other data source that is changing over time, because then
like Spark or how to map reduce systems or things like that. I imagine it would be more prominent in distributed systems, right?
Mm-hmm. Yeah, something like that. And so you pull in that data, and you might not have indexes, might not be the same because a row got removed or something like that. And so what they're basically saying is you can take a hash of the data, so you have some small representation of it. It's just some string basically saying this is the signature of that row of data. And then every time after that, you can just check the hashes and make sure you're pulling out the identical samples. So anything that looks the same as your first split is still going to be the same data that's pulled out. I've never seen someone do that in practice, but that is kind of the idea of what they're doing.
Isn't that kind of a weird thing for the author to include in this book, though?
Yeah, I mean, I really have never seen someone do that. It's a bit bizarre, but it's probably a useful tool to have and something to think about.
No doubt.
Splitting your data is extremely important.
I would say that it's pretty hard to say that you're going to take best practices for end-to-end machine learning project and fit it in one chapter. So a hard job for the author, and I guess also to certain by extension, Ian, a little bit hard job for you to then try and
it's
cover this in
120
one meetup.
Jesus, it's 120 already.
Yeah,
Okay,
I know.
well,
Time flies.
This is a learning experience. So, clearly I do not know how to actually time or manage this sort of thing.
I love your document. This is awesome stuff. And so actually, thank you for agreeing to allow us to post it, because I think there are a lot of people who get a lot from reading through it. But yes, unfortunately, for time reasons, I think you're going to have to pick and choose a few things to highlight for the rest of this chapter 2, which again, it's a big chapter. It's a very big chapter.
I mean, I'm not super familiar with this second version. Is it the same situation in the first versus the second as far as like chapter sizes? I don't think they changed this one that much.
No, I Ryan, you have the book. I haven't really. I don't remember, but I mean, yeah, some of the chapters they're kind of big.
I think this is one of the longer ones. I was commenting on that right at the beginning. This was a monster chapter.
Well, maybe a better thing to do would be like, okay, so we have this document, you can reference this. The gist of the document is that I combined some of the notes from the book, the good notes that the author gave, along with some snippets from the notebook, because not everything in the notebook is really, that useful. And then it's got some kind of elaboration and tips and miscellaneous assorted things, basically addressing some of the things that I had always wondered, like just things that you encounter. So maybe it would be best at this point to address questions or any difficulties that people have getting up and running, because that would be pretty aggravating for them if they just kind of got steamrolled and then every week there's a chapter and they're like, oh damn.
Yeah, I think that's a good idea. Let's see if people came to the meeting with any specific questions. We can take a couple minutes for that, and then also, I don't know, I'm just thinking, this is in the flow of the book, this is intended to set people up for, look, here's this whole process, and obviously you're going to learn a lot as you become a machine learning or data scientist, practitioner. But as we do these different algorithms, we're just going to kind of hone in on what this algorithm does, not the big picture of like where it fits. So there may actually be an opportunity at some point, maybe in December, we like have a session we kind of revisit, right? Now that you've seen some of these algorithms in action, do people actually have questions on how they kind of fit in this workflow? So we'll see.
You take a high level and then you take a low level and then, that's a good educational approach to it.
Yeah. All right. So does anybody have specific questions either from the chapter itself or from the code, the chapter 2 notebook?
And these can be like just any silly random questions, because there's a lot of miscellaneous things that the author did or showed that weren't really explained.
Can I?
Yeah, Oh, go ahead.
No, go after you.
Okay. Yeah, I don't know. I mean, I tried this chapter on a separate data set that I'm actually trying to turn in this week. It's Indian housing prices. It was in Kaggle from about a year ago. The data set was 4,000.
Mhm.
And so I ran the stratified sampling to split. And it really didn't make that much of a difference, I don't think. I mean, I think.
What did you stratify by? Which group did you use?
It was number of bedrooms in the houses, and so it went from one to 5, and I think the normal or the full data set the highest distribution or the highest percentage was like 0.45, and the what I go ahead.
What you could do to kind of diagnose that is you could do something like a box plot, and if it looks like, you know, through all those groups, if it looks like, you know, the mean and the variance is kind of the same, then, you know, maybe it's not that predictive of an attribute or feature. And if it's not that predictive, then, you know, splitting by it or, you know, stratifying by it, you know, may not necessarily help you, right?
Okay. Yeah. Okay.
Yeah. Briefly, I'm not 100% sure, Harold, where you were going to go with the question, but when you stratify by something, you're ensuring that you get an even mix, right? That you get one bedroom in all of your, you know, samples, and you get, you know, 5 bedrooms in all of your samples, right? If you had enough of them, then you might have lucked out and had them anyway, and so you know, it may not have been necessary. But it's not always going to be the case that stratifying makes a difference. But sometimes if you have, you know, Ian showed there's 5 islands, that's like even way too small because it may not be predictive. But, you know, if you want to make sure that you have enough of a small minority class in all of your, if you're doing folds or samples or whatever, then that's where stratification will ensure that at least you have somewhat of an even spread.
Yeah, I mean, I think the difference in like the biggest, the number 3, I think, was the highest number of bedrooms, and it was like 5/100ths of a, you know, of a percent. I mean, I think it went from like 0.455 to 0.46.
Yeah, so stratification is not designed to change anything. It's just designed to ensure that you don't get bad results. So
concerned about generalization error. So basically, did you evaluate both your model that was trained on stratified data and your model that was not? Because maybe they evaluate on a test set very differently. It would be, you know, you could commonly use both those situations, or, you know, train models on a stratified set and a non-stratified set, and, you know, maybe your train and validation numbers would, you know, look similar.
Yeah, I haven't run that part yet, but I will definitely do that.
Yeah, I mean, that's what you care about ultimately, is, you know.
Yeah. Cool, thank you.
George, do you have a question? If no one has, I have a question about standardized coefficients here.
I had some comments. I can go after you.
Oh, okay. My general question is, you know, whenever we do linear regressions in the traditional statistical analysis world, we look for the standardized coefficients, or you also look at the unstandardized coefficients both. But in this case, I don't see it as a common practice for anyone to look for those things. Well, does anyone have any thoughts about that? Like in terms of,
honestly, I think probably a lot of us that kind of hang out on Kaggle don't really do a whole lot with linear regression and stuff like that. I mean, kind of the trending things are, you know, gradient tree based models, boosting tree models, you know, XGBoost and LGBM. So, you know, does anybody have kind of a stats background that can kind of shed some light?
I'm not sure if Mir is still on. Maybe Mir, you can shed some light here.
Standardized coefficients mean that you run your regression on scaled variables.
Right, like for example, in the housing, I think, yeah, maybe not a typical kind of linear regression, but in any sort of general linear model, right? You definitely can't evaluate that if we are just doing traditional stats. But here, I don't think even there's a package to get to the standardized coefficients unless you're doing R. Is there?
You can scale in Python too, but you know, you just put scaling in your pipeline, then you work on it. So we standardize our data when we have a huge amount of data and you do a lot of operations on them. And it means that you can, if your values are too big or too small, then you run into truncation errors. And these truncation errors can end up and they can bias your result. So standardization helps with it. This is a first thing. And the second thing, if you're doing, for example, logistic or linear regression, some people sometimes consider values of the coefficients and they say, well, this coefficient is greater for this column than for another. So we have more influence from this variable than from another. So I don't know if you do this, but I've heard people doing it.
That's right. That's actually what we hope to do. So Ian, you're showing this, but this is not standardized coefficient. I think
Yeah, I was wondering whether they had some other.
Yeah, we try it on our side. It's actually, there are some approaches in terms of calculating it. I find it quite interesting that most data scientists don't even bring it up.
Yeah.
Yeah. So Becky, I mean, the way I think of interpreting something like a linear regression or GLM is that you have to understand the units of your variable and in order to understand the coefficients. Okay. So if your variable goes from 0 to 100, then a coefficient of 0.01 corresponds to a 1 unit change in your input, right? Whereas if your input only goes from 0 to 1, then a coefficient of 0.01 means something very small. It reflects only a 0.01 change in your input variable. I don't personally, so there's generally a caution around just saying which coefficient is bigger, because you certainly have to understand the scale of your inputs.
But that's why we need a standardized coefficient though, right?
Yes, but I will say that even if you standardize, that to me is still a dangerous practice, because let's say you have, I don't know, something like age and you standardize it, okay? In that case, if you have a wide range of people from 18 to 100, right, the 1 year is going to represent a fairly small increment in your possible values. Let's say I'm just trying to think of something. You have height as another variable, and so then maybe you have in the extreme, people from whatever 4 feet to 7 feet. Okay, so you only have a 3 value difference, right? And so it's true that the coefficients are going to be standardized, but that doesn't necessarily mean that a typical increment in your input is the same, even though you've standardized. Like I might say 1 inch taller is a common increment in height, but 1 year represents a much smaller increment on the standardized scale. So personally, my recommendation is to translate the coefficients back into your original units and to say, so let's say linear regression. So then our prediction goes up by 0.2 for each year of age. Our prediction goes down by 0.3 for every inch of height. Now you can actually truly interpret it because people know what an inch means and what a year means.
Right, I think I totally get that part, but standardized coefficient, to Mia's point, usually, at least in my own experience and practices, it is really just supposed to compare the relative importance of those attributes in the same model. It's not so much about directly translating a unit of increase, so to speak. I mean, what kind of result it will make in the outcome. It is giving us some visibility into, like, I think Harold asked the question about maybe that's not his ultimate question, but stratifying on, let's say, bedroom. If all we're trying to answer is that, is bedroom more important than square footage in driving the model, right? What would be the kind of metric or measure we should look at to evaluate that?
So this may just be my personal opinion, okay? And I am certainly not the strongest statistician, but I would say, again, I would disagree with that. I think that's a reasonable shorthand if you're just trying to do a quick and dirty and understand what's going on, okay? But let's say you standardize on the variance. So you are saying that one standard deviation, if you have a bigger coefficient for variable x1 than x2, one standard deviation of change in x1 is going to have a bigger impact than one standard deviation of change in x2. But what is one standard deviation? If one standard deviation is 1 year of age versus one standard deviation is 5 inches of height, but they're not apples to apples to me.
But it's taking the into consideration of the distribution of your data, right? It's not like if really the one variable doesn't have a ton of variance in the data versus a variable that has a ton of variance that could impact your outcome in a very different way. I think we should capture that, even though they are not, yeah, those variances are not the same at all from the both attributes.
Yeah, I think we're not disagreeing on the principles. It's just a question of, right, like personal preference, right? So for me, you know, I would say that if income is one of your inputs and you have wild variance in your inputs on income, and income also has a very strong effect on your variable, it's still hard to say, well, what does that mean? Because both of those are large, right? When one of them is small, then yes, it does actually, you know, help you say that the effect is small, whatever. But if they're both large.
Got it. So maybe my kind of general question here is really in a linear regression model or GLM context, what would be the measure for you to decide on which attributes are more important? I mean, I get Ian's point about SG boost, and you can still get the importance rank and stuff like that. But in this kind of linear regression context, if we do want to evaluate like which attributes are driving it, how did you do that?
I would say use lasso regression because it drops variables which are not very important. And then you can look at what coefficients get zeroed.
You can certainly do that to drop the less important ones, but the ones that are left, I would say there is no natural interpretation of importance. What you have an interpretation is size of effect.
Yes, and the thing is another thing which are not so definite. The thing is that your coefficients have their own confidence intervals. And just because one coefficient is greater than another doesn't mean that it is more important, because it can have wider confidence intervals, which overlaps with confidence intervals for lesser coefficient. And so in this case, we actually cannot say much.
Yeah, I think that's a very good statement.
I just want to interject because we're over time here. So I think this is actually a good question that we can continue discussing if we want to in office hours time. But I think we also have some stuff to figure out in terms of the book club stuff. So do we want to do a second continuation session here?
I'm open either way. We could take another Saturday. We could squeeze in, you know, pending Ian's schedule, you know, a weeknight, and then for people who, you know, really are only available Saturdays, that, you know, we could make the recording available. Or we could not necessarily do it sequentially. We could come back to it at some point. I don't know. I think those are 3 different options. I could put together a real quick poll if people want. I could do a Zoom poll.
Yeah, I think that would be a good quick thing we could run.
All right, talk about something. Give me a minute because this is not a super fast. It's fast, but not super fast.
I can chime in a little bit. So this is a great session. Thanks, Ian. One thing that you have to keep in mind, I think, is when you calculate all these correlations and scatter metric plots and all that, this is where the dataset size plays a huge role. So let's say you tackle a new dataset from Kaggle and it's tens of thousands or hundreds of thousands. If you try to do this on a Colab or a simple VM, like it might not even run. So this is where you need to think about infrastructure and maybe using other libraries like Dask, for example, or dedicated GPU infrastructure just to run this scatter metrics, if that is really important to your code or your pipeline. And I don't know if the book addresses that later on. I haven't read the next chapters. And the other thing is this capping of values. To me, it's really critical and it can impact your modeling and your performance. So this binning of basically a value is higher than a max value to a given value. That's to me a little bit problematic, maybe with data gathering or data representation. So I don't know if there are any best practice out there. Maybe you represent those data points differently or you scale them differently. I'm not sure. Curious to hear your thoughts.
Yeah, with that capping, I mean, I think in the chapter that gets solved just from doing a little bit of digging. But if indeed, some of those those huge numbers on the edge of the histograms turn out to be actual outliers, would you go back to like an MAE instead of a RMSE type of evaluation? Would you switch at that point? Because you said that MAE, I think you said one of them works better with outliers than the other. And I think it wasn't the one that we were using.
I think it kind of just depends what you're measuring and what you're trying to achieve. The RMSE is going to more heavily penalize if you have extreme error, basically. So if you have something that is 10,000 off or something with RMSE, it's going to end up some colossal value. But if you do MAE, it might be something more reasonable. It kind of just depends. It is measuring slightly different things, but I don't know that you can necessarily say one is better than the other. It's just depending on what you're measuring.
So I just popped up a poll. Do people see it?
Yeah.
All right, so I made it multiple choice. So you can say like, I'm okay with either A or B, and I'll give people just a few minutes. And then I'll show the results.
Oh, you can vote for two of them.
Yeah, I think you might be able to change your answer if you didn't realize that, if you want to. All right. Did most people who want to vote get a chance to vote? Anybody need more time? All right, so I'm going to show the results. So I'm not sure how it looks on your screen, but I'm sharing the results, so you should be able to see.
It was quite overwhelmingly continue Saturday.
So Vibhu, are you okay doing 2 weeks from today?
Let me double check my schedule real quick, but yeah, let me see what date that was.
Yeah,
I'm gonna
next
be,
week.
I think I'm flying out somewhere on the 29th. So that Saturday would actually not work for me. I'm going to be out that weekend, but we might be able to squeeze it in because my session next week, it's like half as long as this one. I think it's mostly just examples of the MNIST data set. So actually, if I remember correctly, there was a bit of theory mixed in there. Like, let me go over it right now. There was some stuff like precision, recall, ROC curves, confusion matrix. So I think with that, plus it can probably be a bit more technical. We can probably like go through Jupyter notebooks of the examples in the book, or I can do a different one on classification. So I can really squeeze that chapter as much as we need to. I'm not sure if everyone, like, are we kind of liking these theoretical sessions, or do we want to do one where it's more like hands-on coding? Like I can go through these MNIST things in Jupyter notebooks during the session, or if that's going to take too much time, I can make notebooks that people can go through on their own, and we can go through some of the more theoretical stuff like ROC curves and all that. So if we need, we can squeeze it in on Saturday, or if we need to push it back, I don't know if someone wants to swap sessions, because the following Saturday I'm flying out somewhere.
All right, I'm going to make an executive decision here. So yes, you're right. Chapter 3 is 20 pages versus chapter 2 is 50 pages. So let's continue this next week, if that works, Ian, and we'll split time. And so I think we can do a little bit of both. And then Vibhu, if you like, again, you know, whatever you think would be cool, if you have like an example separate from the author's notebook that you think, you know, then maybe we won't have time to go through it, but that would be supplemental material that people could play with through the week.
Yeah, I'll make it work. I'll just plan on us doing both sessions.
All right, Ian, you good with that too?
He gave a thumbs up.
Oh, okay.
He was muted, but there was a thumbs up there.
I have a poll covering my screen, so I didn't see. All right, cool. So thanks for all the engagement and all the questions, everyone. If anybody joined us just at 1:30, sorry for going over. Warning, we may often go over by a little bit. So, but yeah, so I think that's a great plan, and I hadn't really looked at how long the chapters were. So we will continue this. We'll give Ian, you know, ballpark half the time to cover, to continue talking about this workflow. If you guys have questions, definitely bring them. And then we'll also cover classification with Vibhu next week. And that will keep us, for all the other presenters, that'll keep us on the schedule so that not everybody has to check their calendars for a new date. All right, cool. So then, Ryan, I think what we're going to do is we'll stop the recording and we will formally transition from the book club to the office hours, the project discussion.